Hello. In my last video on Maclaurin series, you might want to have a quick look at that. We looked at how to approximate one of these functions here, e to the x, or cos of x, or sine of x, at around the point x equals 0. And how did we do that? Well, we matched all our values, didn't we? So let's have a look. This is the equation for e to the x. That's the approximation. So what do we do? Well, we found matched its initial value at x equals 0 of the function. Then we found the gradient and we matched that at x equals 0. Then we found the curvature, our second differential, we matched that. And we carried on matching. So generally, we matched the rth differential here. And it's again got a 1 to get r to the power x to the r. And that worked out pretty well, didn't it? We got this formula down the bottom, a for Maclaurin. So what are we going to do if we're not near x equals a? So x equals 0. What if we're x equals a? Let's have a look. Okay, so let's have a look at the function e to the x. And let's say we're working around x equals 2 and we want to make an approximation. Well, what are we going to have to do for our assumptions? Well, firstly, we're going to match our differentials at x equals 2 now rather than x equals 0 because that's what we're working around. Secondly, our distances would have to be measured from 2. So that our distances are x minus 2. So have a think about it. Here's our curve, here's our point. If I move across a bit to here, this is my little delta x, isn't it? And delta x is going to be equal to x minus 2, because that's just the distance on the bottom of my gradient triangle, isn't it? So what does that mean for our series? Well, our approximation, well, we're going to match our value at x equals 2. We're going to match our gradient x equals 2. We're going to match our second differential at x equals 2, etc. And the second part is, rather than having x here, we're going to have x minus 2, because these are our delta x, isn't it? That is delta x. That's delta x squared. Now here is delta x to the power r. There we go. Okay, so all we need to do is to match the gradients, etc., and equate them. So here as f of x equals e to the x, when x equals 2, then we're just going f of 2 is e to the 2. So first differential, the gradient is just going to be the same, isn't it? The differential of e to the x is e to the x. So the differential, the gradient at the first differential at 2 is e to the 2. Second differential is also e to the x, so that's e to the 2. So if I did that generally, excuse me, I'm just going to move that to there so I can see it all on one page. There we are. So the rth differential here of x is still e to the x. So the value of the rth differential at 2 is still e to the 2. And if I just substitute those values into the equation up here, then I just get this down the bottom. Here's my series approximation. So e to the x, when working around 2, is e to the 2, that's my f of 2, plus e to the 2, that's my f dash of 2, and we're multiplying by these delta x, aren't we? And there's e to the 2, that's my second differential of e to the x around x minus 2, etc. So that's what my series is going to look like. For this one, straightforward, same sort of process as we did for Maclaurin. Let's have a look at what that means graphically. So I'm just going to put up a graph. So my red line here is the curve of y equals e to the x. I'm working around x equals 2, so you can see down the bottom here I've got a black dotted line running up from 2, so we're operating at x equals 2, and A is the point of intersection of our x equals 2 with the line y equals e to the x. And if I'm going to start off with our basic, this is on GeoGebra using the Taylor modeling polynomial. So if I was just matching my y value here, I would get e to the 2, wouldn't I? So I've got a horizontal line, y equals e to the 2. If I match my gradient, there we go. I've now matched my gradient, which is also e to the 2, and I'm still working around 2, you can see. Now if I put my match my second differential, there we go, I've got quadratic, and it's working from that point A. And if I do it for the cubic, there we go, that's my third differential's now matched. My fourth differential, that's my quartic. And as we go along, we can see it's still starting to match, but everything this time was started from around A. Excuse me, I'm just going to go back so we can just see that. Everything is based on the point A that we start with, yeah? All the gradients, etc. are matched there. Okay, and in this case, x equal 2. A of the value of A is 2, yeah, that's what my x value is. Okay, so what if I wanted to generalize what I've just done? Well, if I wanted to find the values of e to the x around x equals a, I'd just match the differentials at a, and I'd measure my distances from a. So my delta x would equal x minus a, wouldn't it? Therefore, I get this form of the equation for the series. I approximate my values, so I equate my values again here, and I get a general differential that the half differential of this function is e to the x, so the half differential at a is e to the a. What does that tell me? Well, that just tells me that my function, my series approximation, would look like that. Yeah, e to the a, that's all my matching my functions, and here's my delta x and my delta x squared, my delta x cubed. There we go. So there you have it. If I was using a Maclaurin series, I would just be finding approximation by finding all the values at 0 for my differentials, and my little delta x, my move away from 0, would be just that, would just be x, wouldn't it? And on the Taylor series, I'm matching everything at a, whatever the value of a is that I want to work out with, and my delta x here is going to be in my x minus a. How far have I moved away from a? And that's all there is to it. Best of luck.